Hello everyone, you are in room 3 now. Nita here as your moderator again for this talks. But first, I would like to introduce the speaker for this talks, Andri Yadi from DycodeX. Oh, okay. Mas Andri, I will read your short profile first, yeah.
Sure.
Okay, Andri Yadi is the CEO, DycodeX, Vice Chairman of Indonesia IoT Association, Physicist, maker, developer, and entrepreneur. Wow. So, okay, and in this session, Mas Andri will deliver talk about TinyML with MicroPython. So the participants, you can put your questions on Hopin's platform because moderator's team will collect your questions there, and I will read your questions here. Okay, please, Mas Andri.
All right. Thank you, PyCon. Thanks again for the opportunity to share in Python conference. It's an honor to be able to, share some topics during this PyCon. I'm going to try to speak in English, but mungkin campur-campur nanti sedikit-sedikit ya. So that this message or this topic can be beneficial for all audience in the world. Okay, let's get started. So the topic would be TinyML with MicroPython. So the idea is how we can run machine learning on low power microcontroller. Or doing inference in machine learning on top of microcontroller with MicroPython. And we will leverage Azure machine learning here so that we can see how we can do end-to-end workflow from the training all the way to the inference. Just a bit about myself. My name is Andri Yadi. I'm co-founder and CEO of DycodeX, also vice chairman of Indonesia IoT Association, Asosiasi IoT Indonesia. And I happen to be Microsoft most valuable professional for Microsoft Azure. So that's why I'm going to talk about Azure here, since this is my area expertise. Like mentioned by moderator, I'm also a physicist. Basically, my background is physics, and but since 20 years ago, I start code, and until now, I still love the code, both for for business, for and also for patient. Right? Since during physics, my final project is regarding IoT, all the way 20 years ago. So it's not yet. There's no IoT yet actually, but it's kind of IoT. So that's why currently my focus both in business and also in expertise is doing IoT stuffs. So just a bit about my company. My company called DycodeX. We are tech startups that currently focused on IoT and AI. That's why this is actually our daily playground for doing TinyML. We've been developing and deploying a lot of products in IoT and AI. So, and just a bit of a story that actually last year I delivered a speak in PyCon Thailand and also PyCon Malaysia. So this year I'm back to the country. So it's an honor, and it's a pleasure to be able to share with you guys, Indonesian fellow. All right, so let me just set a baseline here about. I'm going to talk about IoT, right? Internet of Things. So basically, Internet of Things is a collection of devices, embedded with electronics and software, or we call it firmware, that collect the data around our environment or around our world using sensors, and they communicate each other or communicate to the cloud via some kind of communication network, and publish or receive the data to and from the cloud, right, over the internet. So that's why we call it Internet of Things. And most of these devices actually usually battery powered. So that's things keep in mind. So when you deploy the sensors on the field, they usually battery powered, right? So that's regarding the power consumption for IoT device. So as you can see here, most of the power consumption is contributed by radio, right? So when let's say your IoT device using some kind of Wi-Fi, for example, right, which is consume a lot of power actually. So 50%, or if you don't use display, is 65% of the power is actually consumed by radio. Be that Wi-Fi or Bluetooth or LoRa and something, or NB-IoT, that kind of things. So that's why, like I said earlier, that most of IoT devices are battery powered. That's why we need to be considerate about how our device consume the power, right? That's why we need to be able to, to be to be able to reduce the power consumption, right? So that our battery life will be longer, much longer. Some say we can achieve 10 years battery life in IoT device. That's actually gimmick, right? Because we have to do something about that, right? It's not a magic. So in order to be able to reduce power consumption, we need to reduce the usage of radio, right? How you do that is by transmitting less frequent. Let's say you transmit about 1 hour interval, or probably few times a day instead of few seconds every few seconds, and so that we can use shorter air time, or the time that needed to be transmitting the data. We have to transmit smaller payload size, right? And so that there's a shorter air time. And another thing is that we can use some kind of low power connectivity, or in IoT world, we often heard about LPWA, or low power wide area network. But regarding to the second point, that is actually this connectivity only allows a tiny payload size, right? It's probably about tens or hundreds bytes, right, for every transmission. So that's the way you reduce power consumption, right? So by reducing the usage of radio. So now let's consider some kind of use case, right? We want to be able to classify activity. As we know that right now we are together facing the pandemics. We have to keep our body healthy, right? So we have to be doing a lot of activity, workout. So you're wondering that your Apple Watch or your Fitbit, those devices can classify the activity, right? How long you've been walking, how long you've been standing, you've been working out, and something like that. So how they actually do it, right? So usually for that kind of use case, we collect the data, the raw data from accelerometers, or we call it IMU sensors, inertial measurement unit sensors. And one way to classify the activity is by sending, the raw data to the cloud. For example, you would take raw data from accelerometers. To be able to classify one activity, you need at least 1 kilobyte of data. And you then transmit that raw data to the cloud. And you do some kind of magic in the cloud, and then you'll be able to tell that this person is being walking or standing or sitting, right? So that's the way. That's one way you can do the activity classification. Okay, but if we try to send 1 kilobyte of raw data, for example, over a low power wide area network, LPWA, for example, if you're using LoRa or NB-IoT, yeah, it may take forever, right? And it consumes a lot of powers actually. So it will beat the purpose of low power connectivity, right? And another way is by, due to a constraint of bandwidth and power, we only send the sample or calculated data instead of the raw data, right? So, again, from the accelerometer raw data, you do some kind of magic. You do, for example, you detect the peak value, right? Or you sample some value, or you do some kind of a fast Fourier transform, FFT, so that you can convert the data from the time domain to frequency domain. That's probably okay, right? You can still, to be able to classify the activity, but we may miss a lot of interesting events. For example, on this image, there's some interesting event here, which is not normal, or which is there's probably anomaly there. So still, you lose some kind of insight there, actually. So for that, we need to be able to put some kind of on-device intelligence, right, to do some kind of complete analysis right on the device. So again, from the accelerometer raw data, you do some kind of on-device processing, so that the device can, just right away tell that the person is being, standing, walking, or still sitting and everything. So by that, you only send very small amount of data, right? Probably only 3 bytes for walking, for standing. You can just send those 3 bytes of data. Why 3 bytes? Because we need to tell that what's the data type of this activity, and everything, and then we can still get the result, right? And this may save power and save bandwidth, yet we can still be able to deliver complete analysis, right? So what is this, right? What is this? Is it machine learning? So for on-device processing, what can we do with it? It doesn't have to be machine learning, right? You can do some kind of threshold-based calculation, something like that, but that probably will not really flexible, right? So when we're thinking about machine learning, we often associate machine learning with a lot of servers, big capacity of servers, big CPU, big GPU, big memory, right, and storage and everything. But actually, some of machine learning problems, not all, but some, for example, for classification, to classify, to tell what's really happening right now, and for detecting anomaly, is it normal, is it not normal, or for some kind of forecasting to predict the future, what will happen next, right? So for those kind of problems, actually, we can do the inference or the processing of the machine learning model right on the device, right on microcontroller. So on tiny microcontroller. That's why we call it TinyML, right? So that's the idea of TinyML. So TinyML is kind of a new field, but rising field as an intersection between embedded system and machine learning. So initially, it's the idea came from Pete Warden from Google when they work on TensorFlow Lite, right? Then they come with TensorFlow Lite for microcontroller, and also from Neil Tan from ARM when he and teams work with microtensor. So it's actually TinyML is inspired by OK Google keyword spotting, right? So OK Google keyword spotting is actually not running on the main processor of your smartphone. It's actually running on some kind of DSP chip inside the smartphone, so that it can be low power. So when Pete Warden say, look at that initiatives for OK Google, then he think, why don't we scale out to another use cases, right? Instead of just keyword spotting. And I need to highlight here that the TinyML only focus on inferencing, not the training, obviously, right? Because for training, you need to tweak a lot of parameters, probably 100,000 million of parameters. But when the tweak is done, for only doing the inference, you can actually do that very efficiently on microcontroller, right? And since ML model is just mathematical function, it's simply just vector operations. So microcontroller can execute that very efficiently. But there's a trade-off actually. There's a trade-off between accuracy and speed. Obviously, we need to be able to execute or inference very fast. But there's the trade-off of accuracy, because we need to reduce some kind of parameters, from float to integer, for example, for 4 bytes to 1 byte of integer, in order to gain speed. But the accuracy is still acceptable, right? And all of this is targeted for battery powered devices. Okay. And what you can do with TinyML, you can do like OK Google for keyword spotting, or also known as word detection. You can do you can use it for predictive maintenance, for example, for predict the fault of machinery or breakdown before it actually happened. You can use it to detect whether your water kran di rumah, kran di toilet is actually being opened accidentally, right? Or since we are facing COVID-19, we can use it to detect the cough of the person is actually COVID-19 cough, or just common flu, or anything else. So we can use it for detecting anomaly in terms of the sound, right? And we can use it for object detection. Is there a person face there, or is the person wearing face mask? And you can do it for activity prediction, right? So in order to implement TinyML, we need hardware and software, obviously. For the hardware, we need some kind of microcontroller that machine learning capable. Obviously, as we know, that there are a huge number of microcontroller in our life. There's a statistic that say it's about 20 billion something a year of microcontroller. Billion, right? Not million, billion of microcontrollers is actually sold every year. So obviously not all of those microcontroller that you probably found on your I don't know, on your clock, for example, or on your wall watch, wall clock, for example, that's not capable. But for example, if the microcontroller on your car, for example, or obviously on your watch is obviously machine learning capable, right? So the class of microcontrollers that accompanied by some kind of subsystem to accelerate machine learning. For example, if the microcontroller has some kind of DSP or ASIC, application specific IC, that microcontroller will be able to run TinyML. Okay. And in order to do development, because we're focusing on development here, we need some kind of development board, so that we can just code right away instead of doing manual soldering and stuff. So you can use it. You can. I will talk about this later. And you need arsenal of software tools. You need some kind of machine learning compilers, basically, and you need to convert the model so that it can run on tiny microcontroller. So that's why it's very important to be able to decide with what kind of tools that you can use, right? We need some kind of SDK and library as well. And you need documentation, obviously. You need code samples. It's nice to have pre-trained models so that you can run your TinyML model right away on microcontroller. So let's see some microcontroller that TinyML capable. Most of ARM Cortex are TinyML capable. For example, ARM Cortex M4, M7, or even Cortex A is actually very TinyML capable. Or you can use ESP32. This is very famous in maker world and hobbyists. ESP32 is very actually very complete chip, very capable. So you can run also TinyML there. And there's newcomers from the RISC-V world. There's a K210. I will talk more about this. And like I said, that you need development boards. Okay, so there are a lot of options for development boards. So you can actually use that. You can just purchase and then you can start code right away. Okay. From ARM, there's Nano 33 BLE or OpenMP or Microsoft Azure Sphere. For ESP32, you can have all. Actually, you can use all ESP32 development boards. Or if you need some kind of machine vision, you need to have the camera. So you can use ESPI or another boards that have been onboard camera. And for K210, we can use boards from Scibit. I will talk about this later, and other manufacturer. And the big question is how we can train, right? How we can train the machine learning model that is able to be inference on top of microcontroller. So the general workflow of preparing a TinyML model, you can use your regular framework to do the training. You can use Keras, Caffe, Onyx, PyTorch, right? You can use that, and like you usually do, and then you can optimize. You have to optimize. You can do some kind of compression, or you can remove or replace some operations, right? So what you can do here, you can optimize the model pre-train, I mean before the training, or you can do actually do the optimization after the training, actually, right? So it depends on the model. If there's pre-trained model, then you can just do the optimization after the training. But if you build your model, it's I suggest you do the optimization before the training, right? Then after that, you'll have a TensorFlow Lite, a file format. Then you need to convert that TF Lite file to the a specific platform, right? So I call it intermediate representation file, a machine learning model. You can use C-array byte, right? Or you can use K-model. I will talk about this later. And then somehow you transfer the file to the microcontroller, and then you use inference library that very optimized for that specific microcontroller to do the inference. So that's generally. So if you're using Azure, we can leverage Azure machine learning to do the data preparation, to do the training, and then but somewhere in the middle, when you have the model, you then you do the compression and compression and like previous workflow, right? Okay. So just a bit about machine learning on Azure. You can use Azure ML for to do focus on solution development. So just use pre-trained models. Or if you want to train your own model, you can use popular net framework, PyTorch, TensorFlow, and everything, and you can use it for infrastructure for deploying your machine learning model. Okay, so let's take a demo here. I will switch to Azure Machine Learning here. So first thing, you can create a data set using Azure Machine Learning. So you can import some kind of data set from local file, for example. You can import from CSV. And okay, it will parse your CSV, and you can see that this is the data, right? And then you can do some kind of schema tweaking here, and then create. So basically, the data set will be available for you to train, right? Or you can share this data set to your fellow data scientists or developers. And then after that, you can use this. Actually, I will show you the code, right? So to use this data set, you can use Python SDK from Azure, like this, just like this, right? So I have here. Okay, here I will train the model for doing some kind of human activity recognition. Okay. So I will not run this because it will take some time. So basically, it's just typical training, right? This I want to highlight here. You can import the data set that you imported from the file previously, right? So this is the way you access that data set, and then after that you can convert to pandas data frame, and you can use just regular, pandas data frame, right? And then for this, this is very simple model. You know, it's just I'm using convolution 2D to do the human activity recognition. Okay, and after that, after the training is completed, then the result would be Keras data file, because obviously, as you can see from my model, I'm using Keras for creating the model. Okay. So after that, you will have Keras file. So actually, I already have here. So this is the Keras data file, right? So this obviously cannot be used directly to microcontroller. We need to convert that into TensorFlow Lite. So to do that, I will open the convert script here, just to show you that in order to convert from Keras to TensorFlow Lite, you can do something like this.
Mas Andri?
Yeah.
Sorry?
Yeah.
Can you zoom in your slide?
Okay. So the ininya ya, tampilannya ya. Okay. Is it big enough?
Yeah.
Yeah, but it's
Yeah. Okay. Thank you.
okay. Yeah, as you can see that currently I'm converting from Keras model to TF Lite, right? So here we have the model. Probably I will let's say I rename the okay, let's check it. So the output would be har.tflite, right? Let's check it. Okay, here it is, har.tflite. And now after that, we need to convert the tflite to the specific platform that we want to use. In this case, I'm going to use K model. I will explain about this later. So we use an application called NCC. Right? So let's convert that. It will take some time. Okay, I'm going to drink my coffee while waiting. Okay, so as you can see, it's converting right now, and it successfully convert. So as you can see, the input would be a 2D matrix, 8 by 8, and the output would be 4 softmax result, right? So, so this is the file. So actually, we can download this file, right? We can download this file, and then we can use it in our microcontroller. So that's the way you do the training, data set preparation, and do the training in Azure Machine Learning. So obviously, I'm not, demo the capability of Azure Machine Learning fully, because we don't have time. So let's move to the another topic. So you can use Azure, or you can use another tools. For example, H-Impulse. They provide TinyML as services. They provide very nice, easy to use web UI that you can use to train and to generate your model, and then you can just import it to your microcontroller SDK. But the problem is the big question in our event, right? Can we code TinyML with Python, right? Obviously, the answer is yes, using MicroPython. So what is MicroPython? MicroPython is basically implementation of Python 3, but on this, a small subset of standard library of Python. It's very extensible. It is very customizable. You can build and target a lot of variation of microcontroller. Obviously, this is open source project, so you can contribute there. And the porting has been available for many microcontrollers, be that ESP32 or CAT210, NRF52, and everything else. But there are also some derivatives which is not following the main line of the MicroPython, but occasionally they are in line. There are OpenMP or CircuitPython or MakeSpy. So I'm going to use MakeSpy in this talk. This is one of the board that you can use for developing, vision intelligence or vision machine learning for using MicroPython. You can use OpenMP. This is very good demo from the maker of OpenMP, from the creator of OpenMP. Basically, he used it for classifying smile and frown, right? The expression of your face. And sorry. Another board that or another platform that I want to highlight here is called Scipit, and Scipit makes, and the microcontroller is called K210, right? So just a bit of disclosure here. We are my company is the partners of Scipit Indonesia. So Scipit based on RISC-V, which is very popular right now, dual core RISC-V 64-bit processor. And it has something called KPU, or knowledge processing unit. This is basically the accelerator of deep learning, or CNN. Okay. Obviously, you don't use this directly. That's why you need some kind of, development board, right? So, yeah, this is actually, I just have the meeting with the creator of the chip, K210 chip designer, and also the CEO of the Scipit. They are actually spouse, right? Husband and wives. Very interesting. So I'm going to use this board. We call it Scipit Amigo. The workflow of TinyML model preparation for K210 is basically the same, but instead of after you generate the TF light, you optimize using something called NNC, and the result is the file called K model. So this K model you transmit to you copy to the microcontroller, to the board via SD card or flash, and you can use it for inference. Okay, let's see some demo here for activity recognition. Okay, so sorry. For that, I will show you some. Just a moment. Okay. I'm going to use my smartphone here to show you the demo. Okay. But first, I will show you the code, right? So this is the code, MicroPython code for classifying the activity. So as you remember that previously we have the model, right? We have the model, we call it K model. So this K model, you somehow copy to the microcontroller, I'm going to use this device. Okay, very small device. So you load to flash or SD card. Okay, so you flash or you burn on your flash or SD card, and then you initiate the sensors, which in our case is accelerometer sensors. Okay, so then you configure the sensors, and then after that you can use the sensor data to do the inference, right? Okay, so I will go back to here later. I will let me connect to the device first. So here I have two devices. Connect the first one. Okay. Okay. Now I have the MicroPython prompt here, REPL prompt. So I can use this to run my code. Okay. So let's run it. As you can see that it's starting to load the model and waiting for the first data. So over here, I hold the device. Okay. As you can see that now it said I'm sitting, right? So let's say I standing. Okay, as you can see that it correctly classify my activity as standing. Let's say I'm walking, right? But it's hard to demo walking here because obviously I have to do walking. But yeah, as you can see that I'm walking right now, and then after that I'm just sitting again. Okay, as you can see that the machine learning is able to detect, to classify that I'm basically currently sitting. Okay. So obviously this device you have to put on your pocket. So that's human activity classification or human activity recognition. Okay, so let's move forward to other demo here, my last demo. Regarding the new normal, right? So currently we are facing pandemics. We currently found facing the new normal. So basically, during new normal, you get a lot of headshot. Basically, you've been screened by a thermal gun. So the problem with thermal gun is very slow, and the data is basically losing, right? So you don't record the data, and there's no distancing. So the solution would be contactless automated thermal screening, right? So for that, we built my company, DycodeX. We developed a product called HeatTrax, basically for thermal screening. But since we do the measurement based on face, so we can use it also for face mask detection. So whether the person wearing face mask, and we can do it. We can use it also for face recognition. For example, for presence, for absent, untuk absensi, ya, bisa dipakai untuk absensi. And this is the demo. So for example, this demo show that it can detect the face mask wearing. Okay, as you can see here, when the person wearing mask, there's a check mark here. Okay, but before that, as you can see, before she's wearing mask, that it say that pakai masker, right? So actually, the face mask detection is happen right on the device. So So the photo or the camera doesn't send any image to the cloud. So basically the face mask detection happen right on the device itself, right? Okay, as you can see, it's very fast, right? It's real time basically. And we can use it for face recognition also. While the person wearing mask is very hard to do actually. So this is the device. So what I'm trying to show here is just a glimpse of that feature. Obviously, I won't show the code for the actual device because we're not using the same device actually. But what I'm going to show here is just a glimpse of that feature, right? So first, I will show the face detection. Again, I'm going to switch to my demo machine here. I will change the device. So over here, I have the device. As you can see here, there's the device that I will use right now. It's called a Cypid Amigo. As you can see that, welcome to MakeSpy, right? This is the version of MicroPython. So to do the face detection, I'm going to use this script. Let me connect to the device first. Okay, I just restart the device. So let's run the demo first. Okay, then we explain what's happening there. Okay. As you can see that the device is able to detect my face. Okay. So as you can see here, this is very real time. It's not recorded. Okay. So as you can see that it able to detect my face wherever I go. Okay. And here you can see that the frame per second is quite high, right? Which is 16. Is it quite high? Let's say you use a Raspberry Pi, for example. You only get probably 4 frames per second. 4 frames per second. But for this, you can easily have 16 frames per second. Okay. So that's the face detection. What's really happening there is actually quite similar like previous demo. First thing first, you set up the camera. Okay. I use QPGA, which is 320 and 240 pixels. And then I load the demo from SD card right now. I call it a face detect K model. So the model is right here. So I copy this model to the SD card. And actually, the model is trained using. The model, the model of that model. The architecture of the model is actually YOLO, right? So YOLO P2, YOLO 2. Then as you know, YOLO is quite big in terms of the size, right? So we have to optimize YOLO 2 so that it can it's able to run on this microcontroller. And the size of that model is actually only 389 kilobyte. So that's the size of the model. Okay. So after that, you just take the photo. The stream from the camera, and then you feed into the KPU, and you after that you get the bounding box model. Okay, that's the way you do that. Okay, let's try another demo, which is face mask demo. It's basically quite the same.
Sorry, Mas Andri.
Yeah.
Mas Andri.
Yeah.
We ran out of the time.
Yeah. Yeah, of course. This is my last demo. So as you can see, guys, it able to detect
Okay.
I'm currently not wearing mouse. Okay. So if let's say I'm wearing mouse right now, it's able to detect it's real time, right? I'm currently using mouse and then I'm not using mouse. Okay, very fast. Still descent frame per second, which is 12 frame per second. All right. So that's the demo. So just call to action. You can get to know more about TinyML. You can visit TensorFlow Lite for microcontrollers, or there's a foundation for TinyML. It's called tinyml.org. And there's a great book from Pete Warden, the one that I mentioned earlier, called TinyML. To learn about machine learning in Azure, you go to azure.microsoft.com. And if you want to know about our product, Hitrex, the one that for thermal screening, you visit hitrex.id. So that's from me. Thanks for the opportunity to share here. Silakan kalau ada pertanyaan-pertanyaan. Thank you.
Oh iya. Thank you Mas Andri, but we are run out of time.
All right.
Actually, we have several questions, but we don't have much time here. So maybe you can share your profile so participants can reach out through your social media.
Yeah,
maybe.
sure. I forgot to tell that the code will be published on my GitHub, github.com/Andri Yadi here. And the slide also on my SlideShare. Okay, I believe you can read that, slideshare.net/Andri_Yadi. Okay, so feel free to contact me on my email, Andri@DycodeX.com.
Okay. Thank you, Mas Andri. So
Okay,
the
thank you, yeah.
participants, you can contact Mas Andri by his email maybe ya and GitHub. Oke. Okay.
Yep. Ya, terima kasih Mbak.
Say
Terima kasih
something to
teman-teman semua.
participants, Mas Andri.
Yeah, TinyML is the
Okay.
future. So it's inevitable. So you guys definitely have to take a look and start exploring it. So good luck. Bye.
Oke, Mas Andri. Thank you for sharing and selamat sore.
Sore.